Hello everyone, this is Professor DePaulo. Welcome you back to Site 220, fully online. And today we're going to be talking about Chapter 14, which involves correlation and regression. Normally these chapters are a little bit earlier in the course, but I think the text is arranged in such a way to put correlation towards the end because they do sort of go into the hypothesis testing nature of correlations, which in my opinion, isn't as necessary to go into, but we're going to touch on that in this chapter along with the variety of different correlation coefficients, and then I'll talk a little bit about regression towards the end. So the chapter 14 learning outcomes including understanding Pearson R as a measure of variables relationship. So Pearson R, which is known as the Pearson product moment correlation, is basically what most psychologists use to look at relationships. There's other alternatives to Pearson R, but Pearson R is the major measure that we're going to be using and talking about. It's a measure of a linear relationship, a relationship in which you can fit a straight line to explain the relationship. It doesn't work if your data are nonlinear, like if you have a curve or you have data that fits a more complex pattern. It only fits a straight line, which is the easiest thing to explain to someone. We're going to learn how to compute Pearson R using both the definitional and the computational formulas. We're going to interpret Pearson R, understanding the assumptions and the limitations that it has, test hypotheses about a population correlation with sample, based on the sample correlation, to basically say, is the population correlation different from zero? The null hypothesis is always that the correlation in the population is zero. And I'll talk a little bit about partial correlation, but this is this is really beyond the scope of the course. I'll be talking about Spearman's correlation coefficient. It's called Spearman's rho. It works with ordinal data. The Pearson R works with interval or ratio scale data. So there's a difference in what you can do if you have interval data, ratio scale data versus ordinal data versus nominal data. The point-Biserial correlation, which is when you have one dichotomous variable, so you have one variable coded 0, 1, and the other variable is continuous. The phi coefficient, which is tied in with chi-square, which we're going to be talking about later in the course. And then the linear regression equation and the significance of the regression equation. So correlation looks at the relationship between two variables. So this is the Pearson R, the little lowercase r that you'll see in many journal articles. There's also big R, capital R, and that is the multiple correlation coefficient. That's a correlation among more than two variables. So that's beyond the scope of this course. I'm going to be focusing on only two variables, which is the lowercase r. The correlation coefficient has a range between -1 and +1, inclusive. So -1 means you have a perfect negative correlation. +1 means you have a perfect positive correlation. And those are incredibly rare, if not, I mean, they really don't exist in real research. In psychology, you're lucky if you get a correlation of 0.5, and that would be considered amazing. In the biologies and in the chemistries and physics, you're going to get a lot stronger correlations than in psychology because you're measuring with less error. Psychology is a real difficult field to measure, and that's beyond the scope of the course, really, but we have ideas of how to measure things, but measuring psychological constructs is always uh, a flawed process. It's so much easier to measure things like weight or chemical reactivity, right? Like melting point, freezing point, versus something like intelligence. It's night and day. And so psychology is really, really interesting, but it's also very difficult to do research in. As far as knowing what you're measuring and measuring it with accuracy. the correlation coefficient can be both positive and negative. If it's positive, that means that the two variables that you're measuring, they go in the same direction. So as one increases, the other one increases. As one decreases, the other variable decreases. So they're always going in the same direction, whether increasing or decreasing, and that is the positive correlation. The negative correlation is when two variables go in opposite direction. So one increases, the other decreases. An example of a positive correlation would be between height and weight. So as height increases, weight increases generally, right? And an example of a negative correlation would be the time you spend on Instagram and your GPA, right? So as you increase your Instagram use, your GPA goes down. As you decrease your Instagram use, your GPA goes up. That could be any social media, right? But Instagram is pretty popular now, or Snapchat, or whatever people are using, TikTok. As you increase your social media usage, the GPA generally goes down. So they're going in opposite directions. So that's a negative correlation. And it's only a measure of linear association that you can fit a line to. And linear is important because it's easy to explain. If you have a curvilinear relationship, it's very difficult to explain, unless it's a really simple, like parabola. But anything more complex than that becomes, really a big headache. That's not even worth looking at. So here's an example of data that was gathered between family income in thousands of dollars and the student's average grade overall. And so these data are plotted in something called a scatter plot, and that's on the right. So that's the graph that depicts a correlation, and you should be familiar with these basic concepts from intro psych, right? General psych. As you can see, each dot in this scatter plot represents one person. So it's one person and it's two scores. One score is on the x-axis. In this case, it's family income in thousands. And one score is on the y-axis. In this case, it's student's average grade. And so those two values for each student, you just basically draw a line to interconnect where those two scores are. For example, 31 and 72, the first data point. You find 31 on the x-axis, you find 72 on the y-axis, and you find the point in which they meet, and then you draw a dot. And that's the first dot you see on the lower left. That's 31 and 72. And then you plot each subsequent person as a single point, and you can see the relationship between these two variables in the scatter plot. And as you can see, the relationship looks like as income increases, then grades increase because the dots are going from left to right. They're going upwards from left to right. And whenever you see a pattern that goes upwards from left to right, it's a positive correlation. All right. So if you were to draw a line that best fits this data, which technically is called the regression line, if you were to just draw a line in here, the line would have a positive slope. And if the line has a positive slope, that means the correlation is positive. If you were to see a scatter plot that's going down from left to right, that would be a negative correlation. And if you were to see a bunch of points that were just randomly scattered and there was no pattern at all, that would be a zero correlation or no correlation. And that's shown here in this slide here, positive correlation between weight and men. Oh, income and weight for men. So as income goes up, weight goes up. But if you see for women, it's the opposite. It's a negative correlation in women. As income goes up, weight goes down. So you see for men, there's a positive correlation. For women, there's a negative correlation. Now, that's interesting because if you put them together, if you just looked at the relationship between weight and income across all people of all genders, you'd probably see a zero correlation. You would say there's no correlation between weight and income. And that would be misleading. So sometimes if you just look for a general correlation in the population at large, you're not going to see it. But when you break it up into categories like this, when you slice it up and divide it and then do the scatter plot individually in each group, you're going to see more interesting relationships. And the only way you know that is to actually look for that. If I just look for weight and income and I say, well, overall, there's no correlation, that would lead me not to see this kind of relationship. So it's a little tricky with correlation because if you're looking in the general population, you may not find interesting results that you may find when you drill down a little bit and look within specific categories. So now, could you do a t-test? Well, I guess I would show you if there's a difference in income between men and women. You could do a factorial ANOVA where you have you'd have gender and you'd have weight, but then weight would have to be it would have to be categorized, right? So you'd have to have like underweight, overweight, or you'd have to have like underweight, normal weight, overweight, right? The advantage, so there's a disadvantage in doing the ANOVA to see this kind of relationship because weight would have to then be categorized into multiple categories, right? And you'd be taking a continuous variable and artificially slicing it up into a discrete variable. And so there's a little issue with that. The correlation avoids that because it's looking at continuous variables or it's looking at continuous variables with a dichotomous variable that we'll talk about later. But you could theoretically run this as a factorial ANOVA and then divide weight up into multiple groups and see the relationship that way if you were totally unaware of gender playing a role in terms of the influence on weight on income. So it's just another example of like there's multiple ways to really tackle a problem. Correlation should be like the first thing you look at because it's like the easiest thing to run and easy to interpret. Here's a bunch of different correlations. As you see in figure A, you have a negative correlation, and this would be actually a perfect negative correlation because all the dots fit on a straight line. That means there's no variability at all. When a straight line perfectly fits all your data points, you have a perfect correlation. Now, this is not, you cannot get this in real life unless you're measuring something very arbitrary. Like height in inches and height in centimeters would give you a perfect correlation, but it would also be completely worthless to do that because it's height. Who cares how it's measured? It's going to be the same thing. But if you were doing real research, you wouldn't find a perfect correlation. So this is just an example of what it would look like. In figure B, you see all the dots are scattered around. There's no pattern at all. The best fitting line here would be a horizontal line for this data, and a horizontal line has a slope of 0. So this would be an example of a 0 correlation. In number C, you see a positive correlation. You see the dots are kind of clustered together. They're not on a straight line, but they're clustered pretty closely. So this is a relatively strong positive correlation. And in figure D, you see a slight negative correlation. You see that the dots are going down from left to right, but they're really kind of spread out a lot. So this is a very weak negative correlation. So how do I determine, or how do you determine the calculation for Pearson R? Well, Pearson R is a measure of linear relationship, as I mentioned previously. Ranges between -1 and 1, and it's calculated as the covariance of x and y. So how well do x and y go together, divided by the variability of x and y. So the variability is kind of a way to standardize the covariance. So it's really covariance x and y over variance x times variance y. I should say the standard deviation x, standard deviation y on the bottom. You'll see that as we move on. But it's a measure of covariability, or how well x and y go together, divided by the individual variability of x and y. So to find a measure of the covariability, we're going to calculate the sum of products of the deviations. So that is exactly how it sounds. It's the product of the deviation scores of x and y. So this is very similar to what we did when we calculated variance and standard deviation. Remember when we calculated variance, we found the mean, and then we subtracted the mean from each score, and that gave us a deviation score. Well, we're doing that again, except we're doing that with both x and y. We're finding a deviation score for x, which is each raw score of x minus the mean of x. And then we're multiplying it by the deviation score for y, which is the raw score of y minus the mean of y. And when we multiply those out, we get a product of the deviations. And then we sum up all those products of the deviations. Now, that could be negative or it can be positive because we're not squaring anything here, right? So it depends on the deviations. If both deviations are positive, you're going to get a positive number. If both deviations are negative, you're going to get a positive number. If the deviations are opposite, one's positive and one's negative, you're going to get a negative value. So you can see that the deviations can be both positive and negative when you add them up. So multiply the deviation of x and the deviation of y together, and then add that for each person. And that's going to give you the sum of the products of deviations, which we're calling SP here. The computational formula for this could be a little bit easier, especially if your means are not whole numbers. So if your means are decimals, then this is probably the way to go. If your mean is a whole number, then the previous example is most likely going to be easier to compute. But this is the alternative formula, the computational formula, for the sum of the products of the deviations. And it's equal to the sum of x, y, which is basically you make an xy column, you multiply each x value by its corresponding y value, and that gives you the xy value. So multiply x by its corresponding y, and that gives you xy, then add up that column. Very basic. That'll give you the sum of xy minus the sum of the x times the sum of the y's over n. N is the number of pairs of scores, right? Not individual scores, number of pairs of scores, right? Or number of individuals, because each individual has two scores, an x score and a y score, right? Now, once you get the sum of the product of the deviations, which is SP, it becomes very easy to calculate correlation. So the correlation is simply equal to the SP, the sum of the product of the deviation scores, divided by the square root of the sum of squares of x times the sum of squares of y. And we've done sum of squares countless times, right? It's the deviation scores squared, and then you add them up. So you find the deviation score, you square it, and then you add it up for x. You find the deviation score, you square it, and then you add it up for y. And those are your sum of squares. And then you take the square root of that product. So a very basic way of calculating the correlation. If I put it all into one big formula, it would look really scary because there'd be lots of different parts to this. But if you do the sum of the product of deviations first, and then you do the sum of squares second, and then you put it together, it becomes a very basic formula like this. Sum of the product of deviations divided by the square root of the sum of squares of x times the sum of squares of y. So you'll be doing this in the practice problems online in the Mind tab. And that will get you up to date on doing this. But this is basic as you've done it all before. All you're doing differently is the sum of the product of the deviations. And that's just multiplication. Now you could also calculate Pearson R by computing z-scores and then multiplying the corresponding z-scores together. So if you computed all your x values into z-scores and all your y values into z-scores, you'd find the correlation in the sample by taking the sum of the product of those z-scores. So the sum of zx times zy all over n minus 1. And in the population, you would just divide by n. But most of the time, we're using a sample because we don't have all the population data. This get you the same answer from the previous slides, but it's a lot more work because to find the z-score, you have to do each score minus the mean divided by the standard deviation. So that's a real big pain. And you're doing that for every score, x and y, and then you're multiplying it all together. It just seems like a huge ask. It seems like more work than necessary, but you could do it this way. If you had the z-scores already, you can compute them. But probably, the only way you're getting the z-scores, if you're doing them by hand, that's great, but most of the time you're not. You're doing it on the computer, and then you don't need the z-scores because the computer will just calculate Pearson R in like half a second. So, and even Excel will do a correlation table for you in less than a second of like hundreds of variables. So there's no need to really do this stuff by hand. The goal of the course, though, is to teach you both the conceptual stuff, which I'm going through in the lecture, and then the computational stuff, which you're getting mainly through the homeworks and through the tutorials in MindTap, where you're just basically drilling down this stuff. The conceptual stuff is much more important, and you see that on the exams because I give you way more conceptual stuff. I give you some problems, a few problems, but maybe like 25%, 20% of the test is problems. Most of it's conceptual because, to be honest with you, you're doing most of the computations through the computer. What's more important is that you understand the concepts, you understand how the computation is done on a basic level. But I'm not going to just, give you these long problems and just ask you to, I just don't really believe in that. Although as a student, I did quite a few long problems by hand, some of which took me over an hour to do one problem. And I thought it was helpful. I'm not quite sure I use it now, but it's good to be able to do things computationally by hand. In your head too, you can do things, because I think we rely as a society. I'm not going to be here talking about society, but as a society, we're relying too much on automation, computers, using calculators for everything. I think doing the calculations on your own is helpful in the learning process, rather than saying, "Oh, it's like a magic box. I hit this button on the computer and I get an answer." It's nice to know how you got that answer, even if you're not doing it yourself, how it was generated, rather than being like the magic box. So that's my sort of PSA for this week. Let's look at question 1 here, learning check 1. A scatter plot shows a set of data points that fit very loosely around a line that slopes downwards to the right. So the line is going downward, left to right. So the data points are going downward, left to right, but the data points fit a line very loosely, which means that they're spread out a lot. So that shows me that it's a weak correlation because the data is fitting the line loosely. So the data is spread out, that's weak correlation. And if it's going down from left to right, that means negative. So it has to be weak negative correlation. And the only weak negative correlation here would be D, negative 0.35. And obviously that's the right answer. So the closer the data points are to the line, the stronger, the bigger the magnitude of the correlation, which is the strength of the correlation, right? And obviously the direction in which the points go. So if the points are going downwards from left to right, it's negative. If the points are going upwards from left to right, it's positive. And if the points are showing no direction, they're just kind of spread out evenly, and there's no pattern at all, it's 0. And then how close the data points fit a line, a best fitting line, would indicate the strength of the correlation. The closer the data points are to a line, the closer it is to positive or negative 1. And just remember that the negative is not weaker than positive correlation. The negative and positive are just directions. They're equally strong. So like a correlation of negative 0.80 is stronger than a correlation of positive 0.70 because the negative 0.80 has a larger magnitude. It doesn't matter that it's negative. We tend to think of negative numbers as less than positive numbers. It doesn't matter in terms of correlation. Let's look at the second question. True, false. A set of 10 pairs of x and y scores has sum of x equals to the sum of y equals to the sum of xy equals 20. So they're all the same. They're all 20. So here you have to go back and you have to find the formula for the sum of the product of the deviations. So the formula for that was sum of xy minus sum of x times sum of y over n. And you're going to plug in 20 for all those values. So when I plug in 20 for sum of xy, I get 20 minus 20 for x, 20 for y, sum of y. So it's 20 minus 20 times 20 over 10. So it's 20 minus 400 over 10, which gives me 20 minus 40, which gives me negative 20. So the answer is negative 20, therefore that statement is true. Second statement. If the y variable decreases when the x variable decreases, the correlation is negative. Well, no, because they're going in the same direction. When x and y go in the same direction, it's always positive. When x and y go in opposite directions, it's negative. So in this case, x and y decreasing would be positive, not negative, so that's false. And this is what we get. You can see the first problem worked out. 20 minus 20 times 20 over 10 gives you negative 20. And obviously, if variables go in the same direction, you've got a positive correlation. So what is a correlation used for? It's used for a prediction. It's used to establish validity, which means that the thing you're measuring, the variable you're measuring, is really assessing what it claims to measure, right? Reliability, which is consistency over time or over applications. And theory verification, like if you have an idea and you're testing a hypothesis, you can use a correlation to support the hypothesis. Correlation describes a relationship, but remember, this relationship is not causality. So correlation is never causation, because there could be another variable or multiple other variables that are really driving the relationship. You know, and everybody talks about the famous ice cream and crime correlation, that there is a positive correlation between ice cream consumption and crime. You've probably heard this one already. I've talked about it a million times in my intro courses, and that's a true correlation. There is a positive correlation between ice cream and crime, but that doesn't mean that one causes the other. So it's not as if you eat ice cream, you become a criminal. It's not as if you're a criminal, you need to eat ice cream. What's driving that relationship is a third variable, the temperature. It's hot out. So when it's hot out, people eat ice cream. And when it's hot out, people commit more crimes because they're outside. And you know, when you're outside more, there's going to be more criminal activity. So you have to be very careful interpreting the correlation. It's not causation. It just means there is a relationship. Causation requires an experiment, and you need to then use random assignment to manipulate an independent variable. That requires a lot more work. Correlation is very basic, but just be careful drawing conclusions from it. Here's another one with crimes. This is churches and crimes. So here there's a positive correlation between number of churches and number of crimes in a particular area. And obviously that doesn't mean that if you go to church, you become a criminal. It doesn't mean if you're a criminal, you're going to go to church. It just means that there's more people, right? So the fact that you have a more densely populated area means you have both more churches and more crimes. So be very careful drawing conclusions. I mean, obviously you might say, well, that doesn't make any sense. But sometimes two variables go together. There's a positive correlation or a negative correlation, and it seems to make sense. And you say, oh, it has to be this. No, it doesn't. Just because it makes sense to you doesn't mean it's causal. It's not causation. So be very careful because you see there's stories in the news, in the media, online. You see tons of bad information online. Be very careful when you read about correlation. Are they taking it too far? If they're saying this causes that, you know that they're making an error, an inferential error. Correlation is never causation. Now, in terms of the range of the correlation, the correlation coefficient is affected by how much data you're looking at. So if you're only looking at part of the correlation, or a restricted amount of data, you may underestimate the correlation, as opposed to looking at all the data. So a restriction of range, which decreases the variability of scores, will generally also decrease the correlation coefficient. So be careful that you're looking at the entire picture and not just part of the picture. That means you're looking at all the data and not just part of the data. Here's an example of restriction of range. Let's say I'm only looking at people on the high end of whatever variable I'm looking at, right? If I'm only looking at the high values of X here, I can look at that group of only people that scored very high, and it looks like the correlation within that high group, which is circled here, is 0. Whereas if I look at all the data points, both the low and the high scoring people, there looks to be a positive correlation here. So this could be something like, for example, IQ and performance. So IQ is the X and performance, the grades or whatever, as the Y value. Well, if we get to the very high end of IQ, IQ is not really making that big of an effect on grades, presumably because once you get above a certain IQ, it's not your IQ anymore that's going to boost your ability level. It's the amount of time you put into something, right? And so there's no real difference. You can have your Mensa person, and you can have someone that has an IQ of like 10 points less, and there's not going to be real impact of IQ there on grades or performance. Whereas if you go to the low end of IQ, performance is really going to suffer because those people don't have the basic ability. They don't have the tools needed to really learn because they're having cognitive problems. So if you only look at the high end, you miss that relationship. Whereas if you look at the whole data set, you see the relationship. So that's the problem of restriction of range. If I only look at part of the X variable, part of the range, I may not get the true meaning of the correlation. And generally, the correlation is going to be smaller when I restrict the range. You also have outliers. Outliers can distort your correlation, especially if you have a small sample. So if you have an outlier, which is a data point that doesn't belong with everything else, it's extremely deviant, and you have a small sample, then the outlier is going to impact the correlation. If you have a large sample, then one outlier is not going to have the big influence. But with a small sample, one outlier could have a big influence on the correlation. And you can see that here. So if you look at the graph under A, you have a very weak correlation with these 5 data points, near 0. And now if I throw in an outlier, the person that scored 14 and 12, way at the top in graph B, all of a sudden the correlation becomes much stronger. It goes from near 0 to near 1. So that one outlier pulls the correlation way out, distorts it. Now that point has a big influence because there's only 5 data points. 6 with the outlier included. If I have a large sample, though, that one outlier is not going to have the same influence. The outliers have a bigger influence with a small sample. So just be aware of that. As mentioned, the correlation measures the degree of relationship on a scale from 0 to 1. This is not a percent or proportion, so you can't really interpret the correlation coefficient in terms of percentages, but you can square that correlation coefficient and then interpret that in terms of percentages. So when I square my R, my correlation coefficient, I get R squared, and R squared is the coefficient of determination. And that R squared value, you can interpret as a percentage. It's a percentage of common variance that these two variables share. So the coefficient of determination measures the proportion of variability in one variable that can be determined from the relationship with the other variable. So my R squared is the proportion of variance in Y that can be accounted for by X. And that plays a big role in terms of when we talk about regression. So how much of the variability in your Y variable can I explain by my X variable? And the stronger your correlation is, then the bigger this R squared value is going to be. Obviously, if your correlation is 1, then you explain 100% of the variability in Y by X. But that's very unusual, right? That's not going to happen in real life. If your correlation is 0.5, which I mentioned as being a pretty decent correlation in psychology, square 0.5. If you square 0.5, you get 0.25. So a correlation of 0.5 only accounts for 25% of the variability in Y by X. That's not good. That means 75% of the variability is not explained by X. That means there's a lot more going on than just X leading to Y. And that's another reason why we can't say cause, right? If X is only predicting 25% of the variability in Y, then X certainly can't cause Y. That would be crazy, right? X is only accounting for a small percentage of the variance. So even with a correlation that we would be very happy with in psychology, 0.5, which I consider a strong correlation in psychology, I'd be thrilled with 0.5 in my data. There are data sets that don't even get 0.5 in a correlation. As I mentioned, because psychology measures with a lot of error, because it's hard to measure things in psychology. That's why our correlations are smaller. That only accounts for 25% of the variability in Y. That's not good. That's why when you look to try to explain a behavior or a phenomenon in psychology, you're not really looking at two variables. You're not looking at what is called a bivariate correlation, which is what we're doing here. Does X and Y go together? Yeah, that's nice. That's good for an intro course. For this course, it's good because you're learning what a correlation is. But in the grand scheme of things, in terms of research, I would never just have one variable correlated with one other variable. I would want many variables. Because if I'm trying to predict Y, I need more than just X. Especially in psychology with my correlations being smaller, I need more than just X. I need X1, X2, X3, X4. I need 4 or 5 variables, maybe even more, to try to correlate with Y. Because I want more than 25% of the variance to be explained. So when I'm building a model, which I do with regression, I need multiple predictors to really get at the relationship I'm trying to explain. With one variable, there's a lot I'm not explaining. And that's the importance of R squared. So don't look at R as sort of, is this really, it's a strong correlation. Okay, what does that mean? Look at R squared. How much of the variance are you predicting? What percentage of the variance are you predicting in Y? What percentage of the variance of Y are you predicting by using X? So that's getting you a better estimate of how important X is. So that's going to come back to the regression later on. Here are 3 correlations, 3 scatter plots of correlations. Shoe size and IQ, you see this correlation is near zero because the best fitting line would be a horizontal line, and that horizontal line would be the mean of IQ. So when you have a correlation of zero, the best predictor is going to be the mean of Y. So the mean of Y would be the best line to fit here, the mean of IQ. So there's no relationship there, shoe size and IQ. If you look at college GPA and IQ, you see a positive relationship. It's, I guess, moderate. It's not very strong because there's a lot of spread. These dots are kind of spread out. But there's a clear positive relationship there. And if I look at annual salary and monthly salary, it's a perfect relationship. It's perfect and positive. But it's also meaningless, right? So, knowing your monthly salary is going to, tell you your annual salary, but it's not something that kind of gives us any information, right? So it's a perfect relationship here, but it's redundant. And that's what I said before about if you're having a correlation of 1, it's not really telling you much. This doesn't tell me much. It just says that, yeah, annual salary is perfectly related to monthly salary. Yeah, we knew that already. So it's a perfect correlation. It's perfectly useless in my opinion, though. It's obviously a positive correlation too, so it's positive 1. All the dots are on a straight line. Now, if I'm testing the Pearson correlation coefficient, I'm using my sample and I'm testing the correlation coefficient in the population. So the population correlation coefficient is given by the Greek letter rho, which is that little p symbol. That's the population correlation coefficient. The sample correlation coefficient is r. So I'm always testing against 0. I'm not saying I. We are always, because everybody does this, we're always testing against the null hypothesis of 0. So under the null hypothesis, there is no correlation in the population. That's H0. So P equals 0. The alternative says that P does not equal 0. And if you have a directional hypothesis, you can. But to be honest with you, no one does a directional hypothesis for correlation. It's never used. You don't have to necessarily test the correlation, but it's kind of useful to show that your correlation is large enough. So if your correlation is really small, it may not be significant. So you may not be able to reject the null hypothesis here. But as the correlation gets bigger, you almost always are going to reject the null hypothesis. And of course, the sample size is important. So if you have a small correlation with a large sample, you're going to reject the null hypothesis because hypothesis testing, in this case, we're going to be using t-test, is very sensitive to sample size. But the magnitude of the correlation is not sensitive to sample size. It's just the hypothesis test. So here's the hypothesis test. It's going to be distributed as a t-score. So t equals r minus p. Now p represents the null hypothesis here, and p is always 0. So you can just get rid of p. Just change it to 0. So t is going to be equal to really r, because p is 0. So it's r over the square root of 1 minus r squared divided by n minus 2. And the degrees of freedom for this test is n minus 2. So that's how you find the critical value. And that will get you your t-score. And then you can see if that t-score is significant. So if that t-score is more extreme than your critical value, you would then reject the null and say that the correlation is significant, which is just another way of saying the correlation is not 0 in the population. Does that give you a lot of information? If you say it's not 0, is that important? I guess that means there's a relationship. It just means it's not 0, so there's a real relationship in the population. I don't know how useful that is, but people do test the significance of the correlation, and all the computer programs will also test it. Now, if you're going to report the correlation, you want to report whether it's significant. You want to give the value of the correlation. You want to get the sample size, which is given by the degrees of freedom usually, and the p-value. And almost always it's going to be two-tailed. There's no point in doing a one-tailed test of a correlation. If your correlation is not large enough to reject the null with a two-tailed test, it's useless. So why do a directional test? I know the book talks about directional, non-directional, but no one does directional tests for a correlation. And here's an example of how it's written up. R is negative 0.76, N is 48, P is less than 0.01, and obviously two-tailed. You can also put the degrees of freedom here if you wanted. So you could put R parentheses 46 equals negative 0.076. And if you put the degrees of freedom in parentheses after R, that's perfectly fine too. I mean, I kind of prefer to do it that way, but you couldn't do it both ways. This is fine as well. Now there are several alternatives to Pearson R. So remember, Pearson R is a linear relationship, and your data has to be interval or ratio scaled. If you have a nonlinear relationship, or if your data is not interval or ratio scaled, then you can't use Pearson R. So other correlations have been developed for these specific occasions. The first one we're going to talk about is Spearman's row, or R subscript S. Spearman's row is a correlation among two ordinal variables, which is ranks, right? Rank ordered. So ordinal, there's a rank order, and the distance between the points on the scale are not equal, right? So like the distance between first and second doesn't have to be equal to the distance between third and fourth, for example. So if you have a scale that does not have equal distances between points on the scale, but there is a rank order, it's going to be ordinal. In psychology, it's not generally there's not too much ordinal data. Most of the data we're using is interval, which you can use Pearson R for. But I guess if you were doing something like class rank as a variable, or your rank you finished in a race, or your rank you finished in your law school or med school, you could use Spearman's row. You could also use Spearman's row in the case where you have nonlinear data and you want to use ranks instead of the actual values of the data, because the data is nonlinear. And so you're trying to find an alternative to Pearson's R, because Pearson's R is for linear data, and you have a nonlinear relationship, then you could try to use Spearman's row too. Here's an example of a nonlinear relationship where you could use Spearman's row. So as long as the direction of the effect keeps either increasing or decreasing. As you see here, this is not linear. You see this logarithmic or exponential curve. This looks like a logarithmic curve. As you see that as x increases, y is increasing too. So you see that relationship keeps increasing. So as x is increasing, y is increasing. So as long as you have both variables going in the same direction constantly, which is a monotonic function, so it's constantly either increasing or decreasing, you can use Spearman's row to give you a measure of this nonlinear relationship. So you definitely don't want to use Pearson's R here, because there's no straight line. It's a curved line, right? So if I use Spearman's row here, I'll get a measure of the correlation between practice and performance, even though it's nonlinear. And this could be interval or ratio scaled. It doesn't matter. If it's nonlinear, you can't use Pearson R. So try using Spearman's row as long as the pattern is either increasing continuously or decreasing continuously. And here we have a pattern where you have increasing continuously from left to right. If you have a more complex pattern where you have increasing and then decreasing and then increasing, guess what? Spearman's row is not going to work. Spearman's row will only work for a nonlinear relationship that is either increasing or decreasing continuously. And this is an example where it would work. Whether this is a common data pattern, it could be. You see this sometimes where you see kind of a logarithmic or an exponential or, a curve where you see that there's either increasing or decreasing and it keeps going. This would eventually become asymptotic though, which means it would basically approach a limit where it would cross. On the left, you see also another graph of a monotonic function, an increasing monotonic function. It's nonlinear. As you can see, it's definitely not a line, but you see that it's always increasing. So as x is increasing, y is increasing continuously from left to right. So I can use Spearman's rho to find the correlation here. And the reason why I can do that is because the ranks, so if I do, I rank order each x and I rank order each y, the rank orders are going to be linear. You see that graph on the right. So the relationship between the rank of x and the rank of y for these four people form a straight line. And so if the ranks form a straight line, I can use the ranks to compute, a correlation, which will be Spearman's rho. These are relatively simple nonlinear curves. Anything more complex where you have increasing and decreasing, as I previously mentioned, you wouldn't be able to do this. Then you could do like curve estimation, and you could try to find an effect, but it becomes much harder. And the problem in psychology is not that you can't fit a curve. So if you have a nonlinear relationship, you could fit all kinds of nonlinear curves. You could fit parabolas, you could fit logarithms, exponential curves. You could fit cubic, quartic, quintic curves, right? Where you have all kinds of bends in the curve to fit a data set. The problem with that is, just because you could fit the more complex nonlinear curve to your data doesn't mean you could explain it. So you might be able to explain, a parabola, but I wouldn't even know how to explain a cubic. It's, and then something more than that, it's going to be even harder. Like an S-shaped curve, it's going to be hard to explain that. So a lot of times in psychology, we don't want to look at nonlinear relationships, not because they don't exist, but because we can't explain them. And the purpose is not just to fit a curve and say, look, I fit the curve to the data. This curve fits our data, the end. That's not how it works. In research, you have to do the data analysis, but then you have to explain it. You have to explain what you found. And if you just say, I fit the curve, the end, that's not explaining what you found. And other people are going to be like, I don't understand what the hell you're talking about. Yeah, you found a curve that fits your data well, but does it make any sense from a real world perspective? Can I interpret what this means? The answer is no. So we have to be very careful about, overfitting our data with all kinds of more complex curves because we can't explain it. And so the best thing to do is try to fit your data with a line. Try to find a linear relationship. If you absolutely can't explain your data and you can explain it with a quadratic function, like a parabola. Parabola is like a big U, either upside down U or a regular U, right? That's a parabola. If you're going to explain it like that, then you can explain it like that. But anything that goes beyond a parabola becomes much more difficult to explain. And so you have to really weigh, like, do I really want to go there? Even though I get a stronger statistical result, I can't really explain it to my audience. And I might not be able to explain it to myself. So this is similar to what I said last time about factorial ANOVA. You want to run a two-way factorial, but once you start going to three-way, four-way, you might find interesting results, but you can't explain them. You can't make sense of it. So there's a limit to how much we can do because we have to do things in a way where we can explain it to other people. Now for Spearman's row, when you're dealing with ordinal data or the monotonic function, nonlinear function, chi-scores need ranks, and so you assign the mean for all your tied scores. So if you have a chi-score between 1, 2, and 3, you'd find the mean of 1, 2, and 3, and that would be 3, 2, 1, 6 divided by 3 is 2. And then those first three would be rank 2, rank 2, rank 2, because that would be the mean of the first three, 1, 2, and 3 ranks. So if you have tied scores and you're ordering them from lowest to highest, you need to replace the rank for the tied scores with the mean rank of those tied scores. And then once you do that, you can then compute Spearman's row using this formula where D is the difference scores. So when you rank X and Y, D is the difference between the X rank and the Y rank for each individual. So if they rank 1 on X and they rank 3 on Y, then D is 1 minus 3, it's negative 2. So it's the difference in ranks between X and Y for each individual. And then you're going to square those differences because that gets rid of the negative number. And you square those differences, add them together, and then multiply that sum by 6. And once you multiply by 6, divide that product by n times n squared minus 1. Compute that fraction, then subtract that total from 1. So there's a couple steps here, but it's nothing too complicated. Just requires finding the different scores, squaring them, multiplying by 6, and then dividing by the n times n squared minus 1. Subtract that total from 1. And that gets you the Spearman's row for ordinal and certain nonlinear data. Now another alternative correlation is the Point-Biserial Correlation. This measures a relationship between two variables where one of the variables is continuous, which means it has many values, and the other variable only has two variables, so it's what's called dichotomous. Dichotomous means only two values. Also referred to as binomial. There's a binomial distribution. We didn't really talk about it, but it exists, and when you only have two outcomes for a particular response, like flipping a coin, would be a binomial event. When you have two values, like heads or tails, you can call it binomial, or you can call it dichotomous. So the Point-Biserial is a correlation between one continuous variable and one dichotomous variable with two values. And it's calculated the same way as you calculate the regular Pearson R. It's the same thing. So you treat it the same way as Pearson R. But it's technically called the Point-Biserial Correlation. Now, if you're looking at the relationship between one continuous variable and one dichotomous variable, it's the same thing as computing a t-test, an independent group's t-test. In that case, you're looking at the difference in the means between the two variables. And personally, I prefer calculating a t-test versus calculating a Point-Biserial correlation, because I find the Point-Biserial correlation to be, I don't know, I just don't find it to be as direct. It seems like sort of a runaround for looking at the mean differences. Yeah, if you have a high Point-Biserial correlation, then there's going to be a difference, right? There's going to be a difference between the two groups. But if that's the point of calculating the correlation, why not just do the t-test? Because that'll give you the exact mean difference. So it gives you more information. It gives me the exact mean difference when I do a t-test versus the Point-Biserial correlation, where it just gives me a value of the association. So I'd prefer running a t-test instead of doing the Point-Biserial correlation, because they're really the same thing. And you can convert the t-test to r squared. So you can convert r squared to t, you can convert t to r squared, and so why not just use t? That's how I feel. But It's out there. You can calculate it. And it's calculated the same way as regular Pearson R. Now, one way to code the dichotomous variable is you can code one group 0 and the other group 1. For example, whenever I code male and female, I always code male as 0 and female as 1. And I can look at the relationship between gender and performance in my class, grades. Is there a correlation between gender and grades? But that correlation is the same thing as saying, is there a difference between men and women in terms of grades via t-test? And I'd rather test it like that. I'd rather look at the mean difference than look at the correlation. It just, to me, it's a more direct way of answering the same question. And you also have the phi coefficient. The phi coefficient is another correlation, but this time it's between two variables that are dichotomous. So both variables are 0, 1. And this is useful for chi-square, which we'll be doing next time, where you're looking at the relationship between nominal variables. So phi specifically is two nominal variables that are both dichotomous. That means 0, 1 for each. You can also calculate something called Kramer's V, which is when you calculate the correlation between two nominal variables that are not necessarily dichotomous. So if you have more than 0, 1 categories, you would use something called Kramer's V. But if you have just 0, 1 for both variables, you would use phi. But they're the same, really. They're similarly calculated. And this can be calculated the same way as you calculate regular Pearson R, except that you have 0 and 1 for all variables, for both variables. Measure of association between two categorical or nominal variables. That's what phi does. Learning check 2. Okay, participants were classified as morning people or evening people, then measured on a 50-point consciousness scale. Which correlation should be used to measure the relationship? So this is dichotomous, morning people and evening people. That's one variable, dichotomous. And then the conscientiousness scale is continuous. So I have one dichotomous variable, one continuous variable. It must be point-Biserial correlation. And that's the answer. So whenever you have one dichotomous variable and one continuous variable, you always have point-Biserial. True, false. The Spearman correlation is used with dichotomous data. And the second one, in a non-directional significance test of a correlation, the null hypothesis is that the population correlation is 0. So with Spearman, we're looking at ranked data. So we're not looking at dichotomous data, we're looking at ranked data. So that's false. And the null hypothesis is true. It always looks at the correlation of 0 in the population. So that statement is true. The Pearson correlation measures a linear relationship between two variables. So correlation is not causation, but it does measure a linear relationship. And since we're looking at the linear relationship, the next question is, can we use a line to fit to that scatter plot, to that data, to that correlation? Can I use a line that I can then use to fit that data and predict values based on that data? Now, this is not causation because there's a direction of the prediction. So X is predicting Y. Y is not predicting X. X is predicting Y. So I'm using my X variable to predict my Y scores based on the relationship between X and Y, the correlation between X and Y. And how well does that line fit the scatter plot, fit the data points, fit that relationship? Obviously, the stronger the correlation, the better the line is going to fit the data points. So here's an example of a regression line. There's my scatter plot between SAT scores and grade point average. It's positive, and since the dots are kind of clustered together pretty well, it's a fairly strong correlation, fairly strong positive correlation between SAT and GPA. Now, that doesn't mean that SAT scores cause you to have higher or lower GPAs, because we know that GPA, there's a lot of factors that influence GPA other than just SAT. But, in the admissions office at many of these universities, SAT scores is what they have, right? This is what everybody takes. So it's a common metric, and they use it as a prediction tool. Now, some people use it too much. Basically, they put cutoff scores, and they say if you don't get above a certain SAT score, we're not going to even look at your application. I think that's wrong, but there are many universities and many Ivy League universities and high-level institutions that do this. It's a way of weeding out people, cutting down their workload, so they don't have to read every application. But there is a correlation between SAT and GPA. It's not causality. However, can I use SAT to predict GPA? So based on your SAT scores in high school, can I predict your GPA your first year of college? And to do that prediction, I need a regression line. I need a line that best fits this relationship between SAT and GPA. And you see it here in blue. And that line has a positive slope, which means that the correlation is positive. And my prediction will occur on that line. So if I'm trying to predict GPA, the predicted value will be on that line. That's where the predicted value will lie. Now, our actual scores are not going to be the same as our predicted scores. The only time that would occur is if the correlation was 1, perfect correlation. So there's going to be some errors in prediction. So we have to keep that in mind. Prediction is not perfect. Unless your correlation is 1 or -1, prediction is not perfect. There's going to be some error. How much error is okay? It depends. Now generate the regression equation. It's a straight line. We need to fit it to the equation of a line. So remember in algebra you had y equals mx plus b, where m was the slope and b was the y-intercept. In statistics, we changed that equation slightly. It keeps the same format, we just change the letters around. So in statistics, we use the equation y equals bx plus a. So your predicted y value on the line, the line value of y, right, equals b, which is the slope. So b is the slope of the line, x is your x value, your raw score for x, plus a. A is the y-intercept. So in this equation, b is the slope, a is the y-intercept, and x is the score you're going to predict from. And then y is your predicted score. X and y are obviously variables, they change, and b are constants, they stay the same. So here is a regression between number of months and total costs. So obviously the more months you pay into something, the greater the total cost. That makes sense. So you see it's a positive relationship, and you need at least 2 points to make the line. Here you have 2 points. You have a 0.3, 80. You have a 0.0, 35, which is your y-intercept. So the y-intercept is always given from the line. It's always when x is 0, that's your y value is your y-intercept. And you also have a value here, 8, 150 something. You need at least 2 of these points on a scatter plot to make a straight line. You need 2 points to make a line minimum. And so you need to find 2 points by plugging in x into the regression equation. You need to find 2 points to find the line and draw the line in. The regression that we're doing is an equation describing the best fitting line for a set of data points. This best fitting line minimizes the prediction errors. So the line that we're drawing is the line that minimizes the errors in prediction. The errors in prediction are the distance between each point. It's the vertical distance. The vertical distance between each point and the line. That's a prediction error. So it minimizes the vertical distances between the line and each point. Y hat is the predicted value of y by the regression line. Y minus y hat is the error in prediction. So that's that vertical distance I had just mentioned. The vertical distance between each point and the line is y minus y hat. That's the error in prediction. So you might say, well, why not just add up all the errors in prediction? And that'll give me the total error for the whole regression. Well, the answer to that is because if you do, you're going to get 0. So think of these errors in prediction, think of them as deviation scores. When we computed variance and standard deviation, we had deviation scores. We had x minus x bar, or x minus the mean of x. And when we added those up, we got 0. So the sum of the errors, the x minus x bar, x minus the mean, right? The sum of those deviation scores is 0. So what we had to do was we had to square those deviation scores. And we're going to do the same thing here with the prediction errors. So the sum of the y minus y hat is going to be 0, because some of the errors fall above the line and some of the errors fall below the line, and they're going to cancel each other out. So we need to square all those errors in prediction and add them all up to give me the total prediction error. Now, since the line minimizes prediction error, it minimizes the squared error in prediction technically. This method is called the least squared error solution, or it's called ordinary least squared, so OLS regression. And there's other forms of regression, but this is the one that we use the most, and it's the easiest one to explain. We're finding a line that minimizes the squared errors in prediction. It's called ordinary least squares regression. And here's a graph depicting what I just said. Here's your prediction line, y hat equals bx plus a. The vertical distance, y minus y hat, is your error in prediction. And we're trying to minimize the total squared error in prediction, because if we add up all the regular errors in prediction, we'll get 0. So we want to minimize the total squared error in prediction. So our regression equation is y hat equals bx plus a. The slope of the line can be calculated with the following formula. The slope b equals the sum of the deviation, products of the deviations, or SP. So SP, remember from the correlation, is the numerator. So the sum of the product of the deviations divided by the sum of squares of x. X is the predictor, so x is predicting y. So you always have to have sum of squares of x in the denominator. Or, if you have the correlation already, you can simplify it. B, the slope, equals the correlation times the standard deviation of y divided by the standard deviation of x. The first formula is going to be easiest because you don't have to compute standard deviation. You just compute sum of squares. So I think this first one is the preferable one if you have that information. And the y-intercept, which is a, is calculated as the mean of y minus b, the slope, times the mean of x. So if you've done the correlation, it's very simple to calculate the regression line, because you have the numerator of the correlation is the SP, and in the denominator of the correlation, you have sum of squares of x. So you can find the slope really easily. And then once you find the slope, you just need to calculate the mean of y and the mean of x, and you'll get the y-intercept. So it's pretty basic going from the correlation to the regression. Here's a regression line, y hat equals 2x minus 1. So 2 is the slope here, and negative 1 is the y-intercept. And you see the individual scores as dots on the scatter plot. And most of these dots are close to the line. I mean, the only one that's farther away is the one at 6. 615 is a little bit farther away. The slope of the line is obviously positive, so it's a positive correlation. Now, if I want to find the total error in prediction, I can do that by finding the sum of y minus y hat and squaring those differences. Right, so if you square the errors in prediction, y minus y hat, and you add that up, you're going to get your total squared error in prediction, which we're calling sum of squares residual. So basically residual is error. So this is the total sum of squares in error that we're getting in prediction. Sum of squares residual. Now if I want to find the average prediction error for each point, I need to find the standard deviation of those prediction errors. And to do that, I can calculate the standard error of the estimate, which is equal to the square root of sum of squares residual over the degrees of freedom, which is n minus 2. So find the squared error in prediction, y minus y hat squared. So y minus y hat is the error in prediction, square it, square that error in prediction, add up all those squared errors, see the sum sign outside there, and then divide that by n minus 2 and take the square root, and that will give you the standard error of the estimate, which is basically the standard deviation of the error. It gives you an average amount of error in prediction overall. So what's the average error across all the data points? And that can help you determine whether your regression line is helpful, it's useful, or it's not so useful. Now, the stronger the correlation, the smaller the error in prediction, and therefore the smaller the standard error of the estimate. So the larger the correlation, the smaller the error in prediction, so the SS residual is going to be smaller, and if the SS residual is smaller, then the standard error of the estimate is going to be smaller as well. The other thing to note here is the standard error of the estimate is going to be smaller as your sample size goes up, because n minus 2 is in the denominator. When n gets very big, this fraction gets very small. So if I have a big sample, that can also reduce the standard error of the estimate. Here are two scenarios. One is a very good fit, perfect fit actually, and the other one is not so perfect. So the perfect fit, where there's no error in prediction, is in figure A. Y hat is x plus 4. And you see that the correlation there is perfect. It's positive 1. And the data points all fit along a straight line. So there's no error here in prediction at all. Obviously, that's not going to occur in real life. And in figure B, you see larger errors in prediction here. So the vertical distance between each point in the line is the error in prediction. And you see there is quite a bit, there is some error here. I mean, more so towards the lower end than towards the higher end, but there's error in prediction here. So this correlation is obviously not positive 1. It's still positive, but it's not positive 1. And by squaring these errors in prediction and adding them up, and then dividing by n minus 2, and taking the square root of that, I will have then the average, the standard error of the estimate, which is the average prediction error. So as R gets bigger, closer to 1 or negative 1, the standard error of the estimate goes down. We can also use the correlation to find the sum of squares of the regression and the sum of squares of the residual. So R squared times the sum of squares of Y gives me the sum of squares of regression. That basically tells me how much of the variability of Y is predicted by X. So how good is X in predicting Y? That's the sum of squares of regression. If I want to find the error in prediction, I need to find the sum of squares residual, which we calculated before, but you can also calculate it with R squared. So 1 minus R squared times the sum of squares of Y gives me the sum of squares residual. So I can then calculate the standard error of the estimate based on R by putting in 1 minus r squared times the sum of squares of y, which is the sum of squares residual, divided by n minus 2, taking the square root. So this is an alternative formula using the correlation coefficient. And then using r squared, which is the coefficient of determination. I could then test the significance of the regression. Just like I tested the significance of the correlation, I could do the same thing with the regression. And this is similar to analysis of variance, where I'm computing a mean squared and I'm computing an F ratio. And the null hypothesis is that the regression line slope is 0. And if the slope of the regression line is 0, that means the regression line does not help me make any predictions. It's useless, basically. It's not even worth looking at. So the null is the slope is 0, and the alternative is the slope of the line is not 0. To calculate the mean squares, I need mean squares regression. I have to take the sum of squares regression divided by the degrees of freedom of regression. And for the mean squares residual, I need to find the sum of squares of the residual divided by the degrees of freedom of the residual. And then the F ratio is the mean squares of regression divided by the mean squares of the residual. So I know that my sum of squares of y can be partitioned into regression and residual. The regression is r squared times the sum of squares of y. The residual is everything else that's left, 1 minus r squared times the sum of squares of y. And I know that my degrees of freedom can be partitioned into regression and residual. The regression degrees of freedom is 1, and the residual degrees of freedom is n minus 2. So degrees of freedom regression is always 1. So let's answer a couple of questions to close this out. A linear regression has a slope of 3 and a y-intercept of 4. So what is the line? If the slope is 3 and a y-intercept of 4, it's going to be y hat equals 3x plus 4. That's the regression line. Y hat equals 3x plus 4. If I then want to find the predicted value of y for x is 7, all I do is I plug in 7 for x. So if y hat is 3x plus 4, and I plug in 7 for x, then y hat equals 3 times 7 plus 4. 3 times 7 is 21, plus 4 is 25. The answer has to be 25. And 25 is the answer by just plugging in to the regression equation y hat equals 3x plus 4, plug in the value of x to find the predicted value of y here, right? So if I plug in x into the equation, I find the predicted y. The y is on the line, on the regression line. Now that might be different than the actual y value for someone, and that would be an error in prediction. Side of the following statements are true and false. It's possible for the regression equation to place none of the actual data points on the regression line. Okay, so can you have a regression line where none of the actual data points are on the line itself? And the second statement is if R is 0.58, the correlation, the linear regression equation predicts about 1/3 of the variance in the y-scores. So the first statement, where you can have a regression line with no actual data points on it, is true. You can. Obviously, you're going to have prediction error because none of the data points are on the line. But there's no requirement that all the data points be on the regression line, because obviously if all the data points are on the regression line, then the correlation is 1 or -1, and you have a perfect prediction. You have no prediction error, which is not a realistic scenario. So there are many occasions where none of the actual data points fit the line. That just means you have prediction error, which is normal. And the second statement, if your correlation is 0.58, to find the percentage of variance accounted for by x in predicting y, I need to find r squared. So square 0.58, and you get 0.336, which is about 1/3. So that answer is true. So you always square the R to get the proportion of variance in Y that is predicted or accounted for by X. And so that concludes this chapter on regression and correlation. It's not a difficult chapter. There's a couple of equations in here. Conceptually, it's important to know the difference between correlation and regression. Remember that correlation is bidirectional. That means there's no direction of the effect. You know, X can lead to Y, Y can lead to X. It just means there's a relationship there. Regression, there is a direction. There's a prediction. So I'm using X to predict Y. But just because I'm predicting doesn't mean it's causal. Prediction is not causality because there's still other variables that can influence the result. The only way you have causality is you run a controlled experiment where you eliminate all the other variables that could influence the result. That's the only way to draw cause and effect conclusions. And that requires a lot of work. That requires you running a study, an experiment. And the correlation and regression doesn't require that. These are non-experimental methods. So you don't have to run an experiment. You could just get a data set and find correlations and find regressions. And you can understand things about the subject you're researching without doing an experiment. And that's the beauty of correlation and regression is you can get a lot of information without running an experiment. And so that's going to be cheaper. You're going to have more access to more data. It's going to be less time consuming. And then if you do choose to run an experiment, you can run a more detailed, tailored experiment based on the correlation or regression data that you found already. So there's a lot of advantages to running the correlation and regression first before you run your experiment. So you have some idea of what variables go together, what variables don't, and then you can eliminate certain things from your experiment. But the correlation regression is not causal. There is no causation, it's just association. The other thing with regression is once you've done these basic regressions, you can start building more complex models. So we only used one variable, we used X to predict Y, but you can use more than one X. So I can have multiple X variables, multiple predictors, and one dependent variable Y, right? And that can give me a better model than just using one variable. So in real research, it's very rare to use one predictor, and it's very common to use many predictors, multiple predictors. You can use 2, 3, 4, 5, 6, sometimes more. And that gives you a better picture of like what variables are contributing or predicting effectively, which ones aren't, and which variables are more important predictors. And that's done through a process called multiple regression. And then you can go even further from multiple regression and you can put it into something called structural equation model, where you're actually setting up a model and trying to predict different parts of the model through regressions. And so you can have a whole big idea of like, okay, X predicts Y, and then Y predicts Z, and it can be really complex, and you can actually test the model to see, does this make sense or not? And that's part of, more technically called path analysis. And then if you're measuring factors, which is you have explained variability and unexplained variability. If you're measuring with error, you can partition the error in a structured equation model, which is much more advanced stuff, something that you would take on a graduate level, where you're building a model and testing the model to see if the model accounts for, and the model is all based on basically regressions and based on something called factor analysis, which we're not going to get into, but basically measuring how much of this variable are you measuring correctly. Remember I said like there's all kinds of problems in measurement in psychology. You can actually assess how much of the variable am I measuring accurately or validly, and how much of the variable is measured with error. And you can actually separate the explained variance and the error variance out. And it gets you a more precise thing. Now, that's not causality, but it gets you one step to causality. Some people will even interpret a very complex model like this as causal, but I wouldn't say it's causal. It is like a step before causality. Causality is a very complex topic, but you can get really advanced stuff moving forward. So if you're interested in, at all in finding relationships and statistics, uh, you're gonna have to take it in graduate school, obviously, if you go to graduate school. You might have to take it before your college, depending on what four-year college you go to, but you're gonna probably have to take it in graduate school at a more detailed level, and you can make a good career out of it. You'll be in high demand. I mean, this stuff is like really important, and jobs are always popping up that need people with mathematical, statistical reasoning, and talk to me about it. Come talk to me. Send me emails. You want to meet over Zoom? We can talk over Zoom. Uh, Eventually, we can actually talk in my office if I ever get to see my office again. Maybe another year. But if you're around, just reach out to me and say, I'm interested in this sort of thing and I want to learn more about it. Now, or it's interesting, or, I wish I could go more detail, but we're doing it online. It's kind of hard to go into more detail online. And I have questions, but it's kind of hard to ask questions online. Oh, I mean, I understand all that stuff. No one wants to be online for this kind of subject, right? So reach out to me. I'll be happy to get you more information, answer your questions, give you some readings, give you some stuff. If you're really into this stuff, or you think you might be into it, or you want to learn more for graduate school, let me know. I'm more than willing to help you out and get you more interested in this stuff, or get you better prepared to move forward if you need it in the future. So let me know. I'm always available, and I love this stuff, so I'd be happy to talk to you about it. This is basically what I focus on is measurement analysis and more clinical health related applications of it. But I'm very into this data-driven process, so let me know. I'll be happy to work with you. So that's enough for now. Thanks for listening. Hopefully this helped you a bit. Bye for now. See you next time.